Center of Excellences, that is the Center of Excellences, and like Center of Excellence in the 3D printing and A&ML and cyber security, cyber law, and the smart transportation, smart um, grid computing. So these are the some of the benefits what we have got from the ROSA, and the total the college has been actually executed TechCube 1, 2, 3 phases. So altogether 40.68 crores has been sanctioned by the Government of India, Ministry of HRD, which is a World Bank funded project. And the R&D projects, which includes SERB, UGC, Spark, DST, as well as sanction like worth of 3 crore rupees, which are ongoing. The college is progressively developing all the mandatory requirements like NBA accreditation, UGC autonomy renewal, and accreditation of PG, UG programs we are undertaking. So, we recently the any disturbance from my side? Hello?
No, sir.
Yeah. So some disturbance is coming. So this is about the college and the university brief for
Sir, your voice is not audible. Sir, sorry, your voice is not audible, sir.
Yeah. So actually, automatically, I don't know how it is muted.
Yeah.
Just now or previously? Radhika madam.
No, now it is audible.
Okay. So anyway, the 1 week program on ATAL FDP is greatly, immensely, and useful to the faculty members who are actually engaged in teaching and also doing research work. And the only my advice to you is, so while going through the brochure, so there are two things I want to advise. One thing is you can go for functionally graded materials. So what do you mean by functional graded materials? So for example, you are putting a slab. So if slab is of certain thickness, let us say 10 inches or whatever the thickness of there. But half of the slab or 2 inches of slab must be with other properties where the heat transfer should be very low, otherwise it's zero. So that the heat transfer should not take place into the house. So maybe it's a concept of green construction or green buildings. Similarly, walls. So walls also, functionally graded walls must be constructed so that the insulation is provided to prevent the heat transfer to the rooms. So because this is also something related to composite materials, which will also be mechanical engineering professors will deal with mechanical engineering, that is a composite. For example, reinforced concrete. So the reinforced concrete is nothing but a composite material. So within the composite materials, we can agglomerate some other new material to prevent heat transfer into the house and also wherever applicable. So those are called the functionally graded materials. So this is possible with the 3D printing of concrete. So if you go for 3D printing of concrete, so we can have one layer of the thickness is some material with some properties, other layer will be with some properties. So mechanical properties or the mechanical characteristics or heat transfer characteristics, so that the material, the heat transfer will not take place into the house. Suppose if you want more in transfer, accordingly we have to plan for the material to be designed, and this is possible only with the help of the 3D printing, and already some IITs also experimenting. For example, IIT Roorkee and other professors are experimenting construction of concrete with 3D printing. So they are doing experiments. So that leads to the functionally graded materials. That is one thing. Second advice is from my side, the use of natural resources. So because day by day, the natural resources are depleting. So can we go for any artificial materials, or otherwise remix, or otherwise we can use old materials like solid waste management, so that we can reuse the existing material, so that we can reduce the use of natural resources. So these 2 points I thought, no, I would put forth to you, so that you are better knowledgeable persons in civil engineering area. So I just combined my knowledge into the 3D printing, because when I going through, there are functionally graded materials also developed by the civil engineering faculty, civil engineering engineers, so that this will be benefited to the society. So with this, I thank you, the organizers, particularly coordinator, post coordinator, Annapurna Madam, Anuradha Madam, and also head of the department, for sharing my thoughts on the 2 points, and also about the college and university. Thank you very much.
Thank you. Thank you.
Over to Madam Anuradha Madam.
Yeah.
Thank you very much, sir.
Thank you, sir.
Thanks for giving good inputs, sir.
Thank you very
Thank
much,
you,
sir.
sir. We definitely will try to incorporate in the future research, sir.
Yeah.
Thank you, sir. Now I request co-coordinator Anuradha Madam to propose vote of thanks.
I'm Mrs. Anuradha, the assistant professor from Department of Civil Engineering, proposing vote of thanks. I propose vote of thanks on behalf of Department of Civil Engineering, University College of Engineering, Osmania University, and on my personal behalf. Firstly, I would like to thank the ATAL Academy for giving us this opportunity to conduct the FDP. I would like to thank the chief guest of today's function, the Principal, University College of Engineering, Professor Sriram Venkatesh sir, for addressing the gathering and giving valuable inputs for the FDP program. I would like to thank our HOD sir, Professor Anjaney Prasad sir, for encouraging and supporting in conducting such FDP programs. I would thank all the resource persons for giving their concern to deliver the expert lectures. I would thank all the faculty of Department of Civil Engineering, all the technician, office staff for supporting this FDP. I would like to thank the designer of this program, Professor Annapurna Madam, who has taken utmost care in designing the FDP in such a way that it will be useful to all the sessions of the participants attending this program. At last, I would like to thank all the participants for making this program successful. Thanks to one and all.
Thank you. Thank you, madam. Now I invite first session, resource person of first session, Professor K.V.L. Subramaniam, sir. Sir just arrived.
Good morning.
Good morning, sir.
Sorry, my video is not working, so we'll have to put up with that.
Okay, okay.
Audio, I think, is perfectly fine. So.
Yes, I request student volunteer to brief about, sir. Dipti.
Yes, ma'am, 1 second. I'm here to introduce Koluru V.L. Subramaniam sir. He has done his PhD from Civil Engineering, Northwestern University, Evanston. MS from Civil Engineering, University of Toledo, OH, USA. His BTech from Civil Engineering, Indian IIT, Delhi, India. Sir's work experience from IIT Hyderabad. He has worked as a professor since 2018. He has also worked as a HOD of the Department of Civil Engineering. He has worked as the Dean in Planning and Development. Sir, active areas of research being structural engineering and concrete materials and structures, behavior of concrete structures, alkali activated cements and alternate binders. Uh, Sir has received several awards and recognitions. He has done the inaugural Professor Dinesh Mohan Memorial Lecturer in Central Building Research Institute, Roorkee. He has got a Teaching Excellence Award from IIT Hyderabad. He has got Outstanding Young Researcher Award, Guru School of Engineering in 2006. He has also participated in National Science Foundation of USA. Thank you, sir, for being in our midst.
Sir, good morning. Good morning, sir.
Good morning. Good morning. Good morning. Yeah, thank you for the introduction. I am sorry, my video is not working. And also to save on the bandwidth, I think it may be best if I keep the video off. So again, thank you, Dr. Annapurna, for arranging this FDP, giving me a chance to talk about something I'm passionate about. Thank you, Anjane Prasad Garu. Thank you to the Department of Civil Engineering for giving me this opportunity to present here. So should I start? Can I get started?
Yes, sir. Please, sir.
Okay. Let me start by sharing my screen. Yeah. So yeah, I'm sharing my screen. Hopefully that's visible. Yeah. So it should be in the full screen mode now.
Full screen.
I hope the full screen is visible. Yeah. Okay. So if the full screen is visible, I'll get started. Let me take my laser pointer. Yeah. So the topic I chose today is concrete processing technology for construction, because I think the FDP is on concrete technologies. And in terms of technology today, the most rapid advancement is happening in processing. And I'll highlight what I mean by saying processing. I think somebody has to turn off their microphone. That will cut down on the echo.
Yes, sir. Yes, sir.
Yeah. Okay. Is that clear?
Yes, sir.
Yeah, thank you. So processing, I want to highlight on processing, and hopefully at the end of my talk, I'll have conveyed to you that now we're talking about processing concrete. It is no longer the 1:2:4 concrete or the 1:3:6 concrete that I was taught. Today, concrete has come a long way, and we are expecting performance from concrete. So with that, I would like to start. And basically, this is a slide I used to motivate on this topic, and that is, this is the skyline as it has evolved over the years, and starting from 1930s up to today. And you see that on the extreme right were the buildings, the tallest building of its time in 1930s was the Empire State Building. And then as you start coming to the left, this was bettered by the Sears Tower in Chicago in 1970s. Then, of course, we came to the Taipei 101, and now, of course, today, as it stands, Burj Khalifa Dubai is the tallest building. Rough height is about 800 meters and a little over 800 meters. Now, few things that I want to point out here. If you look at the extreme left, 1930s to about 1970s, 80s, even 90s, the building structural systems, the main structural system of the buildings was steel. And that was because people, could not produce concrete that would meet the performance, could not make concrete that was strong enough. And what was worse was we did not have technology to deliver concrete. So we did not have means to lift concrete to say 500 or 600 meters. And that was a big stumbling block. So, but what is happy to note is if you start moving to the left and you start coming into the 2000s and start more into 2010s and 2020s now, we see that the structural systems are concrete. So if you look at Burj Khalifa, the main structural system is concrete. And that has been possible because of advancements in concrete. Now we are making concrete that is stronger. We are making concrete that is longer lasting. It is able to deliver performance. And we are also able to deliver concrete at 800 meters height. We have now developed technology that we can place concrete at 800 meter height. So this is advancement that has happened. And this has only been possible because of processing. And processing, we are now paying a lot of attention to processing in producing this high performance material. And broadly, if you look at the processing, we are looking at processing in two stages. One is processing in the fresh state. We expect our concrete now to perform even in the fresh state. And performance, once concrete is hardened, once it is in service, we also expect high level of performance from concrete at that level. So now we are being very clear about these two things. So with that, let me just give you a snapshot of how things stand. If you look at super tall buildings, most of the new super talls are found in Asia. Now, if you look at 100 of the tallest buildings in the world today, 59 of them are in Asia, 23 are in the Middle East, leaving only 18 in the rest of the world. That tells you that the technology as it is being applied to high rise and super talls is all happening in Asia, Southeast Asia, and Middle East. Not in Europe, not in US. For once now, in technology lead has happened or is taking place in Asia. The other important thing is that if you look at the two of the tallest buildings, Burj Khalifa and the new 1 kilometer tall Jeddah Tower in Saudi Arabia, the structural systems are made of concrete. And that means that now we are able to rely on concrete to deliver the performance. This is a bar chart that shows you how things have progressed. 1930s, blue, light blue is steel. And if you look at the share of steel in buildings, particularly the super tall buildings, that has gone down to the level that it is only 9%. Pure steel buildings are only 9%. Whereas concrete and composite now occupy a very large share. Of course, composite is coming in a very strong way at about 57%. But even concrete is 30%. And even composite, it's primarily concrete used with steel. So that is now happening. And like I mentioned before, all of that has been possible because we have made advances in strength. Now we are able to make super strong concrete. We have made advances in pumpability and construction techniques. I'll talk about these in the next few slides. And you cannot beat the affordability of concrete. When you compare steel with concrete, concrete wins hands down. Concrete is, you cannot compare with concrete in cost. So therefore, we are developing economical solutions which are cheaper than steel, delivering the same performance. So that is the key thing. So, and all of that is only possible through processing. That is the key thing. Just to give you a little bit background again, just to beat home the point, our current usage of concrete is about 2 tons for every human being on this planet. And it goes into uses like pavements, bridges, dams, of course, buildings, monumental structures. One cannot replace the use of concrete in this in our current world. So now the issue here, of course, is one thing that we are all talking about is cement. Cement is needed to make concrete. And if you look at this graph here, this is the consumption of cement, past, present, and future. Blue is India, red is China, yellow is all the other developing countries, and the developed world is this light blue. And you see where we stand today, India is the second largest producer and consumer of cement, second only to China. But if you project forward, by the time 2050 rolls around, our projected demand and consumption will put us in the number 1 spot. We'll be the largest producer of cement. We will also be the largest consumer of cement. By then, if you see that the demand from China is tapering because They've already invested in their infrastructure. So at that point of time, their demand would go down. And you see the demand from other developing countries catching up. So this is where we stand with our usage of cement and projected use of cement based on the infrastructure that we have to put in place. Now, so this is cement also, because we need such large cement. The estimated requirement of cement is 750 million tons per annum in 2050. It'll be it is so large, in fact, the projected demand, that it is raising concerns. They are projected to last 35 to 40 years. It's the good grade limestone that goes into making cement. Energy requirement for producing cement is high. It consumes energy intensive material. So we have to look for alternate sources of energy to sustain the production of cement. And of course, the large carbon footprint. The cement has a very large carbon footprint. So there's a lot of material technology development that is happening here, where we're looking for alternate cements, where we're looking at reducing the clinker factor in cements. We're looking at alternate binder systems. All of that is happening in parallel while we are working on trying to make our concrete more performance oriented. So just to give you a brief snapshot of what is happening, this is our conventional OPC, where we use clinker and gypsum. We grind them together. Typically, gypsum is about 5%. We have now come to the point where we are using less and less clinker in our cement, which means, of course, less demand on raw materials, replacing it with more waste materials or post-industrial waste materials, and that has already become the norm. But we're going further, where we're looking at new types of cements called LC3, which basically uses low-grade limestone, and with that, then we are able to produce cements with even lower clinker factors. And of course, then there is this alternate line of cements we're producing, which are called geopolymers or alkali activated materials, where we start with post-industrial waste materials like fly ash or slag, and we alkali activate them and make cements or cementitious binders out of them, or I should say cement-free binders with them. And now parallelly, technology is developing on those lines to produce concretes of the future. Now, but one of the major challenges that we face with our construction is we're talking concrete. And one of the biggest problems we have with concrete is the build shapes. Currently, concrete is formed on site. Most of concrete, except the precast concrete, most of it is formed on site. And when you form it on site, then we are limited to rectilinear shapes. That's because we have to pour concrete into a formwork, and the concrete takes the shape of the formwork. And because of the limitation imposed by the formwork, we are pretty much stuck with rectilinear shapes. And rectangular, we know that rectangular shapes are not most efficient. When we talk about a beam, a rectangular beam is not the most efficient beam. An I-beam is perhaps more efficient. But the problem with making rectangular I-beams on site is the formwork. That's a big limitation. Now, perhaps when we talk about different structural elements, the most optimal shape, if I optimize it for performance, or a square or even an eye, it may be something like this. And if this was the case, then I cannot form this on site. Forming this complex shape on site is not possible, which means conventional concrete technology has to be replaced with something which allows us to produce complex shapes and be able to form this on site. And that's where we are all headed towards. And this takes us into the domain of digital construction. We're talking about 3D printing. That means we should be able to print now complex shapes and be able to deliver these shapes, which may be optimized for performance. And that is the key thing. That's where we're headed. And all of that would only be possible if I can process concrete to deliver the performance required for printing. Now, again, coming to this building faster, everybody is talking about building faster. Nobody has time. Gone are the days when we were talking about 30 days or 40 days slab cycles. Today, we're talking about 3-day slab cycles. Now, one of the biggest limiting factors there is the formwork. As you can see here, you have to assemble the formwork, you have to tie the reinforcement, then you place concrete. And you wait for concrete to gain some strength before you can remove the shuttering. That delays the process. So therefore, and of course, it requires a lot of labor. So we have to now advance technology of concrete production, concrete delivery systems, which will allow us to circumvent this problem. And so we're talking about form-free construction. Form-free construction means we are not going to use formwork in construction. It will be free form. We will form our structure on site and it will be literally replicating whatever we have as a design and producing that structure on site. So as we see concrete construction of the future, we want to make concrete responsive to the requirements. That means we want to tailor the delivery and placement, and I'll give you some examples of this a little later. And we want to ensure performance. That is, these are the two key things we have to ensure. We have to tailor delivery and placement. I want concrete to give me freedom to place it in a certain way, to deliver it in a certain way, and I want to ensure performance from this concrete in the long run. So that brings us into performance-based design. Now, more and more, we're talking about performance-based design. And just to contrast with the conventional method is how we have been doing things. This goes into structural design. It also goes into concrete mixed designs. The way we do conventional design, whether it is mixed design or structural design, is we have prescriptive requirements based on strength. We define a strength, and then we have all these rules that we follow, and we come up with something. And somehow strength forms the basis of everything. Somehow we think that if you have concrete of a certain strength, automatically it achieves all these performance. And that is the key thing, is that our focus has always been on concrete material strength and structural member capacities. That's how we do conventional designs. Now we are evolving into performance-based design. And here we want this methodology in which the structural criteria are achieved, are basically stated in terms of achieving a performance objective. We basically now do not place emphasis on strength. Strength is just a byproduct. We are now going to stipulate things in terms of achieving performance. Performance during formation is becoming important. We want concrete to meet certain requirements while we are placing it. And performance during service life. These have become now, or are coming into force, and slowly codes are also being modified to account for this expectation from people. Now, performance specifications. Now, structural performance requirements have already made their way into codes. We are now doing performance-based design for structures, particularly for earthquake and wind design. Now we are talking about performance-based design. So that has already been in practice for some time. But from materials perspective, it's new. Now we're talking about formability. How formable is the concrete? Placement and speed, and of course, long-term durability. To this effect, going a major revision, and we will be introducing performance-based specifications even for material from the material perspective. Concrete mixed design is going to become performance oriented, and that is coming in the code as we go along. The whole point is to basically replicate what you can do from a factory made element. I want something that is of a uniform quality, something that meets my requirements when I'm placing it, and something that gives me high performance when it is in use. Just to give you measures. The performance measures now can be broken into two: fresh concrete and hardened concrete. Previously, we never thought of prescribing fresh performance concrete properties. These were never prescribed before. We only prescribed hardened concrete properties, but now this fresh concrete performance properties have also become important. And we are talking in terms of flow. We expect concrete to deliver certain flow, not just slump. Pumpability has become a very, very important requirement now, and filling ability. This has become very important now. So, and of course, there are additional fresh performance characteristics. And today in my lecture, I'll be talking more about this fresh concrete performance. How do we engineer the material so it delivers on the fresh performance? Then, of course, there are the hardened concrete performance requirements. The key, of course, is strength. This is always there. But we're talking about long-term durability. This has found its way into performance requirements. Now, it's not just enough that we produce concrete of a certain strength or a certain grade. It has to ensure that it is long-term durable, and that is being included in the performance requirement. If I do meet both of these objectives, then I'm given an assured performance. I'll just give you an example of where performance found its way. This is the Union Square building in Seattle, where concrete strength was prescribed. It's not a small value, 131 megapascal compressive strength, but they prescribed a modulus value where the concrete was required, a 41 minimum modulus of 41 GPa was specified. So this is one of those early instances where performance started getting specced into our requirement for the concrete. Now, to give you some more performance requirements, this is Burj Khalifa. and concrete was pumped to 600 meters. Now, if you look at the concrete, we know that it is like a very thick paste. It's like a viscous fluid, and it's a very heterogeneous material. It has aggregate, it has paste, it has water. So pumping concrete to this height is not easy, 600 meters. Now you can imagine the technology that would be required to lift a material which does not want to flow, which is very viscous, to 600 meters. So technology development did take place. In fact, Samsung, the company that took up the challenge of pumping concrete, delivered or developed special pumping systems that would allow concrete to be lifted to the head of 600 meters and above. But more importantly, now I have to make sure this material concrete that I'm going to put in a pipe and pump should be able to withstand the pressure, should remain homogeneous. That means it should not start segregating and separating out under pressure. And when it comes out of the nozzle at the other end, it should basically remain as one cohesive material and fill the form. So that is what is the requirement from concrete, and that is now being specified as a performance requirement from fresh concrete. So here, in fact, if you look at one World Trade Center, concrete is pumped to 103 stories. And in the next slide, I'll show you the performance requirements that put in place. This is the performance requirements put in place for the one World Trade Center. This is a building that replaced the World Trade Center, the Twin Towers. Here the specs were that one could not use more than 236 kgs of cement per cubic meter. This was specified. Contractor could not use more than this. Concrete that went into the columns up to 40 floors was required to meet the strength requirement of 80 to 95 megapascal. And in the upper floors, concrete had to meet a strength requirement of 60 to 70 megapascal. Of course, this is a 56-day strength that was specced out. But performance requirements are given. There was a slump flow requirement of 600 to 710 requirements. Of course, it's flow, not slump. That is, when you do the slump test, it should meet a flow requirement of 600 to 710 millimeters. One should be these are the important criteria. The concrete should have the ability to pump at least 15 floors for 95 megapascal mix, and the concrete should have the ability to pump at least 40 floors for the 80 megapascal mix. That means now this is a fresh performance requirement that is placed on concrete. Whatever concrete that comes to the site, it should be able to meet this requirement. And it was also specced out that the maximum heat of hydration could not exceed 70 degrees Celsius. So now these are all performance requirements. This is what is expected from concrete that comes to the site, in addition to our strength. So strength requirement is anyway there, but these are the additional requirements. And if you look at this performance requirement in the blue box here, these are fresh performance requirements, fresh concrete performance requirements, and these were placed as restrictions or as requirements from the contractor who supplied the concrete. Now, but for this requirement, the cement could not exceed 236 kgs, and that was done in order to reduce the carbon footprint and have a greener concrete. But for that, there were no other requirements. So here, what you're doing is you're freeing the contractor, or you're freeing the material supplier from prescriptive measures. You're not putting anything prescriptive there. You don't care what mix is brought to the site, as long as it ticks all these boxes. If all the performance boxes are ticked, that is what is expected from that concrete. Mix design itself is left to the contractor. You don't specify that this is how much water you should add and this is how much silica fume has to go in there. None of that is specified. But as long as these performance requirements are met. In addition to this, there were also performance requirements for long-term durability. I'm not showing them here, but that was also required to be, or the concrete was required to satisfy those requirements as well. So now, of course, when we're talking performance, then we need tests. Because so far, when we talk about tests, we are limited to what is available in IS 516, and it's a very limited set of tests. Now we need a more extensive series of tests. So when we're talking about, of course, these are the American tests based on ASTM standards, but we are also now slowly bringing in more and more tests into our Indian standards. When we're talking about durability, we need to include things like low permeability, chloride penetration, high resistivity, low absorption. And so for each of these, there are tests. And now what is acceptable criteria are also based on these tests are also given. And these are all long-term durability measures. We pick and choose. So we expect our concrete in the long-term performance. We specify some or all of these as a requirement for concrete. And the concrete then that is delivered on the site should be able to meet these test requirements based on and satisfy these criteria based on these tests. So this is the whole paradigm, or this is the whole concept of performance-based design, where you don't tie the hands down of the person who's making the concrete. Instead, you insist that the concrete that is coming to the site has to meet these performance requirements, and they have to satisfy certain criteria based on these standardized tests. So now, of course, how do we achieve this? So if I now talk about the way we make concrete, the basic combinatrix that I have of cement, water, and aggregate, we cannot achieve this performance just using this basic combinatrix. It is just not possible. So what we need, and of course, what is required from concrete, ideally, if you look at what I expect from my concrete, is that it should be able to flow like water. It should set on demand. It should gain strength rapidly. It should be durable to infinity. It should look like new without any maintenance. And of course, all this should be achieved at a low cost. So these are all the typical requirements of what we expect from our concrete. And the only way that I can meet some or all of these demands is not using just the basic combinatrix. We have to bring in admixtures. And this basic combinatrix, the way we have done it, has really not brought into account packing and some of these advanced concepts. So now when we're talking about concrete mix design, we're talking about packing. How do we pack aggregate? How do we pack the solids in the concrete so that we can develop something that optimizes the cement usage? Then we're talking about admixtures. Admixtures are a must. We cannot make concrete deliver the performance without the use of admixtures. So, of course, there are different admixtures, and broadly, what we add as an admixture is a performance enhancer. It basically enhances the performance. We use these in small quantities, and I can use these to control the fresh properties, and that goes into this broad category of what we call rheology control. And rheology as a field is quite advanced, and chemical engineers have used rheology to control the flow of fluids. Even household chemicals like shampoos and toothpaste have been engineered to deliver the kind of flow that is required. So rheology is a mature field. It's now that we're bringing in rheology into concrete, where we're trying to bring it in to produce concrete that meets the flow requirement that I need. And of course, I need performance enhancement in mature concrete, which is concrete that has gained strength. I need the fundamental preliminary requirement is still the strength, but now durability is also coming into play. So I need to reduce cracking. And so we're talking about admixtures like shrinkage reducing admixtures, super absorbent polymers, ASR mitigators, etc. We need to mitigate the effect of cracking. Suppose concrete does crack, then we're talking about self-healing concretes. We're talking about waterproofing, integral waterproofing, etc. And general durability. I want concrete to be durable. The steel that is inside the concrete should not corrode. So we're talking about corrosion resistance, matrix densifiers, and all of these are coming into use. And today, if you look at concrete, it's a very complex soup of cement, aggregate, and a whole host of admixtures that go into making this concrete. So just to talk about admixtures, I'll just briefly show this. These are basically any material other than the basic ingredients, which are used to enhance or modify the fresh, mixed, or setting or hardened properties. And as you see in this cartoon here, this the person who's producing concrete is saying basically, today concrete without admixtures just belongs in a museum. It just it's not even the most common production of concrete today adds one admixture or the other. And we have a laundry list of admixtures, and I've listed them here. And typically, several of these are combined, and they go into making of modern day concrete. Then what is it that we expect from our high performance concrete? This is concrete that is going to deliver high performance. We, of course, have the basic Portland cement. We're talking blended cements, and of course, we have a whole bunch of other materials that go into it, which includes mineral admixtures like fly ash, slag, silica fume, calcine, clay, metakaolin, etc. Then we have chemical admixtures like retarders, accelerators, and everything else that is added in there. And of course, optimally graded aggregate. Now we're talking about packing and all of that, which is coming into play. So that is about general performance requirement of concrete. Now I'll talk about performance during placement. This is the fresh concrete performance, the processing requirement of concrete. And this takes us into transporting and placing concrete. This is when now we're talking about how do you transport concrete? How do you place it? A lot of emphasis on pumping, like I showed in the previous example. Self-leveling, self-consolidating concrete. This has come along a long way now. We are almost routinely producing this. And formless placement. That is the last step where we want to produce concrete without the use of formwork, which is pretty much taking us into the domain of 3D printing. Now, the most fundamentally important admixture that we use is water reducer. And of course, the need for water reducer came up about 30 years back, 40 years back, when we realized that if I want to make concrete that has a high slump, then I need to add water, but the minute I add water, then I lose strength. So then people invented these water reducers. Initially, they were just simply water reducers, and now we have made these more and more complex, and to the point where we've come to high range water reducers. Now, as the challenge was to get concrete to flow with less water, that was the challenge. And of course, without admixtures, as you see here, we basically get some slump, but with a little bit of water reducer, I can get this concrete to flow. So that was the early thought that went into making concrete that was strong, yet somehow be able to fill the formwork. And this is just to show you, this is rheology control, and I'll explain this a little bit later in a few of my other slides. Concrete without, this is cement paste without admixture. If I mix cement paste, let's say with a water to cement ratio of 0.32, 0.33, or even up to 0.36, it doesn't flow. It just is very tight. But the same cement paste with just a few drops of admixture, water reducer starts flowing. So that is what these complex chemicals do. They enable the flow without having to add water. And just to show you that if I have a concrete without admixture, this is the water demand based on certain flow requirement. I can basically reduce the water demand to produce the same flow with the use of this high range water reducer. Now, what are these water reducers? These are very complex chemicals. And today, if you look at the super plasticizers that are produced, these are very highly engineered polymers. These are polymers which basically have been engineered. Today, typical PCE, the polycarboxylate based admixtures, which are used to provide this control, have a spine, which is a long chain molecule with these teeth like attachments. And this is like a very highly complex polymer system that is produced. And the spine basically adheres itself to cement paste. The comb-like, tooth-like structures stick out, and they produce what is known as steric repulsion between cement particles, so that they do not agglomerate. And by doing so, we are able to produce flow. That is the basis of this water reducers. And this is high level chemistry, where basically one has to understand chemistry to be able to produce these polymers for use. And of course, it should be able to do so without impacting the hydration or the strength gain of concrete. So a lot of work is done, and a lot of it is being done by chemists. So we basically, excuse me, yeah. So we are now talking with the use of these things, we're talking about along the way, we realized that we can, of course, now start engineering the flow of concrete. And here you see concrete being pumped. So very soon people realized that it was not just enough that we mix concrete that has high flow or has a high slump. It should be able to withstand the rigors of pumping. I should be able to pump it. It should be pumpable. And what comes out of the nozzle should still be homogeneous. It should not be that, aggregates stay behind, the water gets pumped ahead, and you create a heterogeneous mix. And then along the way, we realized that, okay, this is not where we're going to stop. We are going to take it to the domain of digital manufacturing, where we say we'll print structures. So that's where we're headed with this processing or the placement performance requirements of concrete. So just to give a little bit of background of where we started paying attention to processing was initially the thought was that if you want concrete to flow more, you simply have to increase slump. Now, when you have a high congestion of steel, even if you have a concrete with a high slump, it is not going to fill the formwork. And as I'm showing you here, this is a typical eye girder, which is a precast girder. And this is high slump concrete, but it just did not fill the formwork because of very high congestion of steel at the ends, particularly at the ends. So that's when people started realizing that slump is not the solution. We need to look at slump different from flow. We need to address the issue of flow, which means that we have to be able to engineer concrete to deliver flow performance. It has to be able to flow. And just to give you another example, this is cast in situ pile, board cast in situ pile, where the reinforcement is lowered into the ground and they pour concrete. And you can see this is high slump concrete, but it still could not flow. It did not flow. So that's when people started paying attention to flow of concrete, and they started engineering the flow, fresh performance behavior, the flow behavior of concrete. And along came SCC, self-consolidating concrete or self-compacting concrete. So this is the genesis of SCC. We want concrete to flow like water. So when I lift the slump cone, it should self-level. It should flow under gravity. It should fill the basically find its own level, and it should be able to flow by carrying the aggregate with it. And this is where the challenge lies, because if I have concrete that flows more, that means I have to reduce the viscosity. I have to make it less viscous, otherwise it won't flow. But if I make it less viscous, then there is a tendency of segregation, because now the fluid phase in the material is less viscous. So there will be a chance for aggregate to separate out. So I need to be able to get this material, this very viscous material, to flow like under gravity-induced stress. It should be self-leveling while it carries the aggregate with it. So this is the key requirement that we have for producing self-consolidating concrete. And that happened by engineering the material. So a lot of work went into packing, understanding the packing, then producing specialized admixtures that will help us develop it, understanding the rheology of the material. So that's when several things came into our lexicon, where we started realizing that I need to understand something called the yield stress of the fluid, something called viscosity of the material, of the fluid. And we need to be able to control both of these to be able to produce concrete that meets this requirement. So this is highly engineered material that delivers this performance of fresh performance of self-leveling characteristic. So that brings us to this field of rheology. We started thinking about rheology. We started paying attention to how liquids behave. And conventionally, when we talk about liquids in the domain of civil engineering, we would only talk about liquids from understanding hydraulics or from fluid mechanics. But we really didn't pay attention from understanding the liquid behavior from the point of view of processing. And this was done, like I said, conventionally has been done in chemical engineering and other fields, but we started paying attention to it, I would say maybe starting from 90s. And we started understanding the rheology to understand what happens when you apply shear to cement paste. And we built from there. So then we quickly realized that there are properties we need to understand. First is called the yield stress, and the other is called plastic viscosity. And these are both rheological properties. And we soon realized that we have to optimize both of these properties. And the way we measure these properties is using a rheometer. And a rheometer is basically a test apparatus where we apply shear to a fluid. And we know that fluids cannot withstand shear. So if you apply shear to a fluid or a liquid, it will flow. And the key is to understand how it starts the flow and how it sustains the flow under an applied shear. So for that, we need this rheometer, which allows us to apply shear in a controlled way, measure the shear as a function of strain rate. So this takes us into understanding of the fluid flow behavior from the initiation of flow perspective and what is required to sustain flow. So this then gets tied into, once I can understand what it takes to initiate flow in the cement paste and then sustain the flow, then I can model, or I will be able to predict the behavior of concrete in our conventional slump cone test. And I can then start distinguishing between slump and flow. So this is the fundamentals of rheology and how rheology made entrance into concrete mixed designs. So what are these rheological properties? When I apply shear strain, suppose I start shearing a fluid. Here is the fluid which is placed between two parallel plates. The bottom plate is fixed. The upper plate is rotated. So as I rotate the upper plate, I start shearing the liquid, this liquid between these two plates, and I measure the response of the shear stress resistance that is generated in the material. If you do that, and I'm applying shear strain at a constant rate, so I'm shearing the material at a constant rate, what I typically get from cement paste looks like this. Initially, the shear stress increases, reaches a maximum, and then it basically comes and levels off at some constant value as I keep on increasing the applied shear strain on the liquid. So this kind of interesting behavior where initially the resistance increases and then levels off required some understanding. And now we understand that this peak here is identified with what is known as yield stress. This is called the yield stress of the liquid. It's not of the solid. And under increasing strain, eventually I attain a steady state. This is where the liquid starts flowing in a steady state. What is happening up to this point here in this box that I've shown here is called the transient state. The liquid doesn't immediately start flowing when I start applying a strain, shear strain to it. Initially, it gives resistance just like a solid. And that is why we get this property called yield stress. And that resistance, I encounter increasing resistance until it hits a maximum called the yield stress. Internally, what is happening? Now we understand that cement and all these cementitious materials have an internal structure, because cement, when it is sitting in water, basically forms a network of solids, cement grains inside this inside the paste. It's like a very dense suspension where I have these solid grains of cement sitting inside. And if I idealize them as shown here, as I initially start shearing it, these grains come together. They basically start agglomerating, and they give me an increased resistance. This internal structure that I have, it was able to resist the shear. And that's why I get this increasing resistance. Eventually, if I force it, that internal structure gets completely disrupted, and I produce flow when all these get aligned, and I get steady flow. So this yield, up to yield stress, in fact, the liquid doesn't flow. It is giving me resistance. And this is key to understanding that when I have something like cement paste, which is a very dense particulate suspension, these materials don't flow immediately, even if you apply shear stress to it. And this is key in understanding. The yield stress that we measure from this rheology ties with the slump that we measure, because when I lift the slump, the cement paste does not immediately want to flow, and that it tries to hold on to its shape. And eventually, when the gravity-induced stress in the slump cone increases beyond what it can sustain as the yield stress, then it starts moving. And that's why we get this slump measured in the concrete. So there is this effort which is required to initiate flow. That is the key thing to understand. Higher the effort required to initiate flow, higher the yield stress, more would be the effort to initiate flow. Now, of course, that would come when I overcome the internal structure of the cement inside. What do water reducers do? They basically give me rheology control. What they do is they disrupt the structure. They do not let the structure form. They disperse the cement grains, so cement paste flows very easily. This network is disrupted, so it basically transitions into steady state very quickly. That's what these high-range water reducers do, or water reducers do. Now, there's also another thing we need to understand, and that is, once I have initiated flow, suppose I shear the material, what is the effort required to sustain it? And that is viscosity. Suppose I apply a constant or increasing shear rate onto cement paste. Initially, I'll have to overcome the initial resistance that is shown here. The y-axis is shear stress. The initial resistance is the yield stress. With increasing shear rate, I will basically get an increasing resistance. And this is what we call classical viscous response from any viscous liquid. And the slope of this shear stress versus shear strain rate is called plastic viscosity. More the plastic viscosity, more viscous the material. That means it would take more effort to keep the flow going. So there is one thing which is initiate the flow. The other is this to sustain the flow. How much effort would I have to put to sustain the flow? So these are things that we have to control when we are talking about producing concrete, which we would want to engineer. And final thing that we also realized that there has to be something called cohesiveness of the mix, where once it starts flowing, I wanted to hold all the ingredients together. And that's where we started developing these viscosity modifying admixtures. And what these do is to increase the viscosity of the mixing water. And basically what it allows me to do is to retain all the constituents in suspension, not allow the liquid part to separate out under pressure. It increases, like you see here, cohesiveness of the mix while allowing a high flow. So you have this concrete which is being poured into water, and you can see that the lighter ingredients start separating out, the heavier ingredients settle at the bottom. And that's what would happen if you just typically dump concrete in water. But if I mix VMA, because VMA has this ability to hold all the ingredients together, I can pour concrete and it basically keeps all the ingredients together. And VMAs are also very highly engineered polymers. And the way these polymers are work is initially when these VMA is at rest, it forms these intertwined chains, which forms these long chains, which basically form like a network. And this network prevents any movement of water from within the system. if I apply shear, that is when I start shearing the material, these chains break, they get aligned, and that reduces the viscosity. So initially, while VMA is there, it keeps all the ingredients together because it forms this network. It basically holds on to all the ingredients. And if I shear it, once I start pumping it, once I start pushing concrete through the pump, then it gives me low viscosity. So I'm able to pump it very easily. And then when I bring it to rest again, this network is created again, and it does not allow the water and other ingredients to move out. It forms this network very quickly. So that's what's happening here. So when I'm dropping this concrete through this funnel here, as it's flowing through the funnel, it's being sheared. So that means it gives me low viscosity. It's able to flow easily. The minute it starts coming to rest here, the network is formed again, and then it holds on to all the aggregate and everything. It doesn't allow the aggregate to separate out. So these are all the chemicals that are engineered, and one is able to produce the self-consolidating concrete. I'll just show you a video of what SCC is about. This is about meeting requirements of self-leveling. It should be able to flow like water, fill the form under its own weight. Oh, sorry, I hope this works. Let me just see. Oh, the video is not working. Yeah, so the videos, yeah. This is a video of SCC. This is, as you can see, it has aggregate in it. It flows very easily. And you see the concrete is flowing like water under its own weight. That's how you, these are experiments with engineering concrete that can flow and fill the form by itself without any vibration. So this is one of the ways that we're talking about engineering the concrete performance to meet the early age performance requirement. Right. So, and SCC has been used in now making even things like precast concrete girders with heavy steel congestion. And you can see you almost get a mirror finish of concrete. And because it flows and fills all the gaps, you don't even need vibration, and you don't have this problem of concrete getting stuck where the congestion is high. And now SCC is being used more and more for producing exposed concrete. So here I cut down on the use of paint. I don't need plastering. And it also gives a very good aesthetic look to the surface that is being produced. Of course, we have gone one step further. We've even produced self-consolidating concrete with geopolymer cements. So what I showed you before was SCC made with cement-based concrete. We have also developed SCC with alkali activated geopolymer blends. So you can now also make, with engineering, we can also start making concrete, which is self-leveling with these other alternate binders. Right. So high performance concrete, fresh flow performance is not just limited to self-leveling or high flow concretes. You can have the other extreme. We're talking about engineered stiff mixes for rapid construction. So this is a concrete paver machine. It's an automatic paver machine where concrete is basically dropped front here, and pavement is extruded from this machine. So you can see concrete pavement is being extruded as the machine moves forward, and there's no formwork being used. So what comes out of the machine is basically something that looks like this pavement. To achieve this, I need to be able to engineer the concrete flow. I need to produce an engineered stiff mix. And the performance requirement here is to have a zero slump, and it should have shape retention. It should be able to retain its shape once it comes out of the nozzle. So again, this performance requirement is a fresh performance requirement to meet the requirement of this particular casting or the production procedure that I'm adopting. And this is, of course, can be done using water reducers. Here also I have to use water reducers, microfines, and retarders. So it's a complex combination of all of these that helps me achieve this performance requirement. The other place where we use this stiff mixes is in the precast production. So these are hollow core slabs. As you can see, these have these hollow cavities that run along the length of this pre-tensioned slab. Now, the way these are made is through an extrusion process. So concrete is dumped here, and concrete is extruded. As it's extruded out of here, it is extruded with these holes. Now, it's not made in a formwork. So the concrete that comes out of the machine should keep its shape and should keep the shape of these cavities and prevent concrete from collapsing on itself. So again, here we need concrete which is an engineered stiff mix to meet this requirement. So ideally, what I need is a zero slump concrete with shape retention. And again, these are very complex engineered mixes which meet this requirement of water, which these requirements are met by engineering the mix by using water reducers, microfines, retarders, and even packing. A lot of effort goes into packing of the aggregate to achieve this kind of performance. Now, coming to the final thing of what I want to talk about with the fresh performance requirement is 3D printing. Everybody's talking about 3D printing. Now, what do we want to achieve from 3D printing? Like I said, we want to achieve form-free printing, where I don't want to use form or any kind of shuttering on the construction site, be able to print concrete freely of any shape I want. To achieve that, we really need to understand the rheology. And I use this toothpaste as an example to illustrate what we are after. If you look at toothpaste, if I squeeze the toothpaste comes out of the tube. And after it comes out of the tube, it keeps its shape. Now, just showing you an illustration. Ideally, we want something that is able to keep its shape. I don't want the toothpaste to be runny. But if you look at the rheology of this paste, it has to flow under pressure. That means it has to flow under demand. If I squeeze the tube, it has to flow. But the minute I let go of the pressure, as it comes out of the nozzle, it should keep its shape. So I have to engineer a material that behaves like a liquid when I pressurize it. And when I let go of the pressure, it should start behaving more like a solid. So that is what we have to engineer. And this takes us into the domain of understanding the flow. And this is basically how modeling was done for toothpaste and tubes and a lot of rheology. And this takes us into the domain of computational fluid dynamics. One really needs to understand that to be able to understand the flow fields, the stress states that are produced. And these are stress states that are produced in a liquid that is flowing under pressure. And also to be able to bring in our knowledge of rheology of the material. How does the fluid behave under pressure? How does the fluid behave under an applied strain rate? And then be able to deliver this kind of a performance by engineering the material, by altering its composition, or by using additives like admixtures. So when it comes to concrete 3D printing, we are broadly talking about concrete meeting 3 requirements. We need concrete to be pumpable. It has to go through a pump. It has to produce a non-segregated flow. That means as it's going through the pump, it should not segregate out. It should keep its shape. Once it comes out of the nozzle, it should keep the shape of the nozzle. And I should be able to print one layer on another layer. So it should allow buildability. So once I have deposited one layer, I should be able to deposit additional layers. So the layer that's already been deposited should be able to take the weight of additional layers. So these are all now the requirements. These are all fresh concrete performance requirements now. And these have to be satisfied in order for me to deliver on this form-free construction that we are talking about. So to achieve this form-free construction, again, I have to resort to rheology control, and of course, I have to use admixtures. And now we have to think about an additional property called thixotropy. Now, thixotropy is the property where the internal structure inside a suspension builds up very quickly. It's also called the ability of this the suspension to build its internal resistance. So here's what has to happen. Now, going back to our toothpaste example, if I squeeze the toothpaste tube, we know that it comes out and it keeps its shape. Now, which means that when I pressurize the system, or when I pressurize the thick paste, it flows like a liquid. So once I initiate the flow, what is required to sustain the flow should not take much effort. Then immediately when it comes to rest, it should keep its shape. That means immediately after it comes to a rest, it should form a structure inside that allows me to keep the shape of whatever it has come out of. Not just that, that internal structure should build over time and quickly, so that as I add another layer on top of it, that internal structure builds. And this need not necessarily be related to hydration. It should build internally by other mechanisms like aggregation, and be able to take the weight of additional layers. So this is the property of thixotropy. And we need something that has a low viscosity under flow. And I need something which a high yield stress, because yield stress is a measure of what it takes to initiate flow. So now the reason I need a high yield stress is because after I have extruded the material, it should come to rest and immediately resist any flow, because if it is not able to resist the flow, then it will simply start spreading out. It has to keep its shape. So therefore, it has to have a high yield stress. The effort required to initiate flow should be high. The effort required to maintain the flow should be low, so low viscosity, and that internal structure, which is in the deposited layer, should build up quite quickly so that I can keep adding layers on top of this. And the way we do this is, again, goes into a lot of engineering. We have to engineer the rheology of the cement paste. We are using a lot of water reducers now. We use a lot of nano and microfines now, because this thixotropy, we are realizing that in order to be able to make these cementitious materials thixotropic, not necessarily set, but make them thixotropic. That means the internal structure inside the material starts building up. That I can achieve using these nanomaterials or microfines. And we are realizing now we can use clays, atapalgite and bauxite, the bentonite. These are the clays that we are using to produce this property of thixotropy. So in cementitious systems now, we're starting to add a little bit of clay to be able to get this, so that we can start building on layers to assemble the whole structure. How can we go doing this? So I'll just show you a video. This is a structure that is printed in, this is a structure that was printed in NTU, Singapore, just to show you what this 3D printing technology looks like. So you can print layer upon layer. You see, this is how the entire structure is assembled, one layer at a time, and you can actually print a very complex structure. And as you can see here, I add layers. So the layer that has been deposited before should be able to take the weight of additional layers. And these layers are still fresh, as you can see here, they're still wet. These layers have set. So even the layers that have not yet set should be able to resist the weight of additional layers. The internal structure inside these have to develop to that point. Now, coming to the real challenges in making this 3D printing technology possible for practical use, one of the biggest challenges is inserting reinforcement. And that is a challenge that we are all currently facing. In order for me to make it practical, I have to be able to insert reinforcement. So there is a lot of effort going on co-printing steel and concrete. There is work going on in Switzerland, where they're talking about large-scale printing, where co-printing, they're looking at strategies with the use of robotics. They're working together with metallurgists, mechanical engineers to make this reality. The other applications that people are looking at is printing formwork. So now, rather than say that, look, I will become ambitious and start co-printing steel, I can use this to print the formwork to the shape I desire, and then I can insert steel and I can fill it with regular concrete. So that is another thing that is being thought of. And the final thing is to use flexible reinforcement in the form of textile reinforcement and fiber reinforcement. So that is also being done, where we are thinking of co-processing these flexible reinforcement and making structures with it. A lot of effort, a lot of research is going on in all of these areas. Now, of course, we're talking about making concrete, and now more and more there's talk of this concrete in micro quantities. So here, this is like a mobile concrete delivery system, where I can vary the composition of this even for small dosages. So as I'm placing concrete, I can vary the properties of concrete in the different layers as I'm depositing it by doing a local control here. So you're talking about injecting materials at the delivery point and locally altering the material so that I get variable properties at the local level. So I can now even start thinking about placing variable strength concrete if I need it within the same structural element. So that is what people are now starting to talk about when it is about delivery systems. Final thing I want to talk about with this is now we're getting into active control. So conventionally, the way we get concrete to flow is by vibrating it. When we vibrate it, we basically loosen up the structure that causes it to flow. And that is what we call compaction of concrete. Now, the new paradigm is to get concrete to flow like the way we want, set on demand, using external impulses, electrical and magnetic impulses. So here we are taking help from magnetorheological liquids. These are liquids that are used in dampers, in automobile shock absorber systems, etc., where the liquid has these suspensions, which are magnetic particles, and under the action of a magnetic field, we can basically get it to behave like a fluid-like structure or a solid-like structure. So if I turn on a magnetic field, it suddenly becomes very stiff. If I turn off the magnetic field, it behaves like a fluid. So if we are talking about active control, we're looking at something where we can do a magnetic intervention, get concrete to flow, and then turn on the magnetic field and get it to set. So that's another area of active research where people are talking about with fresh performance control of concrete. And then, of course, talking about electrical control. So not just magnetic control, but in something like a 3D printing, we can talk about inserting this magnetic material inside this printed concrete, and by altering the magnetic field in the nozzle, we get to change the magnetic flow behavior. So I can turn it on, get it to flow like a liquid, turn it off, get it to flow like a liquid, and just as it is being deposited, I can turn on the magnetic field and get it to behave like a solid and keep its shape. So these are all different ideas on fresh performance control of concrete. And again, electrical control. So there's some work that's being done on dipolar molecules where I can use an electrical field to basically control the set and strength gain. So this is where now we're getting into active intervention to control the property development in concrete. So finally, what are the challenges that we have in this performance control and processing to achieve performance? Well, these challenges of producing concrete to meet certain performance requirements can only be met if I start using admixtures. I look at concrete mix design in a scientific way by looking at packing and some of these other aspects. But one of the biggest issues that we face is with the use of admixtures is cost. When I start adding material like admixtures, these are expensive, they drive up the cost. So that is one of those things that is working against us. The other issue that we have with the use of admixtures is that these are black boxes. We really don't understand them. Today, what we buy as an admixture is a very complex soup of chemicals, and it is beyond the comprehension of an ordinary civil engineer. We're simply using it like a black box. And for us to understand chemistry, we are civil engineers. We are not going to go into that depth. And that's where some of these things are getting beyond our control as civil engineers, where these are being produced as black boxes by these companies. We simply add them and we use them without really understanding the chemistry, the engineering that has gone into making these liquids, and what are the limits of where and how we can use these materials. Finally, just like drug interaction, we can have drugs. If you use multiple drugs, there can be some interaction between these drugs. Similar thing can happen with admixtures. If I now start using multiple admixtures in order to control the different parameters, we can have adverse interactions between these admixtures. And those can have undesirable effects. So I can add an admixture that can start impacting the strength. So that's, or it can adversely affect some other durability property. So we need to really understand these admixtures, sorry. And finally, government, when I say government, it is the policy making bodies. Our codes have to be updated for us to use these things. And we have to be bold enough to adopt this performance-based design, where we remove these prescriptive measures and we insist on performance. And that requires a certain level of advancement on policy making bodies. And there are new binders in the market. Everything we are doing so far is based on cement-based systems. But cements are getting slowly replaced with additional material. Either the clinker factor is going down or we're talking alternate binders. So we should be able to, whatever we do in these, the top 3 boxes has to be done for new binder systems also. And the final thing I want to leave you with is that whenever we're talking about new technology, if you just look at the technology, nobody will adopt it. If you look at the face value, that's because it's going to be expensive. Any new technology will be expensive. So if you look at cost today, new technology will not be adopted. So the way we have to make argument as civil engineers for adopting new technology in construction is to talk about cost over benefit ratio. So if you look at the cost over benefit ratio will require an assessment of life cycle, where we have to assess the life cycle of the structure. And potentially what we see is that there will be enhanced performance of the structure. And if you spread the cost over the lifetime of the structure, there will be savings. So that is where the kind of arguments that we have to make for bringing this new technology into the market. So this is what I wanted to present. At this point, I think I'll conclude. Thank you for your attention and probably take any questions that you may have.
Thank you, sir.
Thank you very much, sir. Thank you very much, sir. Thanks for thank you so much, sir. Thank you for your innovative lecture on concrete processing technology for construction techniques, sir. You have given the enriching like information, okay, about the various aspects in the construction technology, sir. I think we have some queries, sir.
Yeah, sure. Are there any questions? I'll be happy to take
Okay, sir.
questions.
128. Madam Usha, ATAL FDP unique ID 128. Please unmute and ask question to sir. $128.
Hello.
Yes.
Madam.
Sir, I have a question that any new technology has been developed in concrete bricks, sir?
Concrete bricks, is it?
Yes, yes.
Yeah, okay. Well, yeah, concrete bricks is a little bit of a misnomer. I mean, conventionally bricks were made with clay, and then we soon realized that
Yes.
it was leading into ecological problems because we were using clay, which was an agricultural resource. So we started looking for alternatives, and then of course there was a time in 90s when we realized that we had abundance of fly ash. So fly ash brick technology came into being. And I would say late 90s and even in early 2000s, a lot of construction took place with the fly ash brick technologies. Different technologies came into market with the use of fly ash. Some used stone chips, some used small stone aggregate, some were used pure fly ash to make this bricks. Then we have since then we moved on to AAC block work, which I think has become quite common now because of the advantages it has in terms of lightweight and thermal and acoustic performance. It gives enhanced thermal and acoustic performance. And those mixed designs were initially cement based. Now they are more fly ash based, but we use a lot of fly ash in making the AAC block work. There's still some cement that is used. Of course, there's autoclaving that's involved. And that has become quite a stable technology now. Going forward now, we are now looking at different forms of brick that are coming in, which with the use of geopolymer. So now alkali activated fly ash cellular bricks are also making their way into the market. This technology, of course, is new. It's being developed. Different groups are working on this. And the matrix here is a geopolymer matrix. So it's made using only fly ash, which is alkali activated. And the curing technology for that has varied. So there are some who are suggesting autoclaving, some use steam curing, some even room temperature curing. So there are different ways in which people are trying to make this particular geopolymer, cellular geopolymer brick.
Yes. Thank you, sir. Sir, instead of this fly ash, can we use some other pozzolanic materials like silica fumes, like that?
Absolutely. The only issue is cost. See, what happens is that at least as of today, fly ash is probably the cheapest pozzolan that's available in the market. Even slag is more expensive than fly ash, and that's the reason why a lot of people, a lot of the entrepreneurs or a lot of people who are commercially inclined are not willing to touch anything that costs money. So if you look at in terms of performance, perhaps you may get the best performance out of metakaolin. But metakaolin is expensive because it is processed clay and that's costs money to make. Slag is again expensive and it's a value-added property, a value-added material that is sought after by cement industry. So it's very difficult to get over slag. Until recently, in fact, there was abundance of fly ash. Lately now, of course, even fly ash is running out because the cement companies are using up most of the fly ash, and a lot of it is going into construction and in roads and pavements and all these other applications. So that's the reason why fly ash is probably more preferred than other materials.
Yes. Thank you so much. Thank you.
Sure.
Thank you, sir. Sir, I too have a small doubt, sir. Sir, I have a small doubt, sir.
Sure.
Sir, you said that the self-compacting concrete can be prepared with geopolymers, alkali activated binders. Because,
yes.
sir, my doubt is geopolymer concrete, when we tried in our lab, actually the consistency of geopolymer concrete will be very less. That means slump we got was very less because no water is added, only the alkaline liquid was added, sir. Because the geopolymer concrete was having a less consistency. With that, is it possible to get self-compactability, sir, for concrete?
Now, this is where rheology control comes into play. See, the thing is, when you talk about alkali activated fly ash or alkali activated slag, typically, at least the alkali activated fly ash would tend to have a higher viscosity than cement paste, but a lower yield stress than cement paste. So these are the two properties which the geopolymer is different from the cement paste. So while in cement paste, we have to use or something which modifies viscosity, a VMA, or we have to increase the fines to basically get the viscosity in control. In geopolymer concrete, we don't have to because it is viscous by nature. So the other thing is with the yield stress. Because the yield stress is low, it tends to flow very easily without much effort. Because it is viscous, it flows like a viscous liquid. It takes a long time to flow. So what we have to do is not touch the yield stress. So we don't need something like a superplasticizer. But we need to somehow be able to see if we can reduce the viscosity. That is the key thing there, is we have to slightly lower the viscosity of this thing. And that you can achieve by controlling the fines, because the fines also contribute to viscosity. So you can achieve SCC with that. So it's all about understanding the rheology of the material.
One doubt is by Sushmita, sir. In case of clay is used, is there no possibility of shrinkage and expansion cracks?
Yeah, that's yes. I mean, that would be the natural thought, right? The reason is because we associate clay with expansive clays, right? I mean, that's typically what comes to mind when I say clay, because we say it's expansive, and as structural engineers, we're taught to be wary of clays because we know that it is expansive. But if you look at clay, and what we use as clay in our applications is a very small quantity of it. So we use like less than 1% the weight of cement. There's a very small quantity, just like an admixture. But what we value clay for is clay, because most clays have large surface areas. I mean, they're basically either plate-like or rod-like structures, which are large surface areas. And clays tend to agglomerate. That's what we know clays for. And when they agglomerate, they hold water. And this agglomeration basically of particles of clay coming together can be broken very easily when you shear the material. Suppose you take clay and you shear it, you rub it between your hands, you'll see that it will start flowing. And that's what happens. So when I put clay into concrete, what happens is If you visualize concrete, you have aggregate and you have paste between the aggregate. As the aggregate move, the paste between the aggregate gets squeezed. And as the aggregates are moving, the paste between the aggregates is also getting sheared. And that is what we have to understand when I talk about the shear behavior of the paste. So when I put this clay in there, when it gets sheared, when it's between two aggregates, the structure gets disrupted and it starts flowing easily. And that's basically what reduces the viscosity of the material. So when I add clay to it, and when I start forcing flow on concrete, or when I start getting the concrete to flow, the clay, basically the network structure disrupts and the viscosity drops, and it basically helps in flowing in an easy manner. But the minute I bring it to rest, when I suppose I bring the concrete to rest, immediately what happens is the clay particles agglomerate again. And when they agglomerate, they basically form like a structure and they lock these aggregate particles in place. So that then gives me a shape. It's able to keep its shape. So that's where I use this clay, and understanding the way the clay works, I'm able to use it to my advantage. Yeah, sorry, coming to the expansion, this thing, A, because I use a very small quantity of it, that is not much of an issue. B, the expansion in clay happens from a different mechanism. And here we are putting it in a very alkaline environment. And if I leave it in the long term, clay typically contains silica and aluminum. These are the two material elements that are present. Clay, if anything, would contribute silica and aluminum to the cement system, because cement systems are also calcium silicate systems. So from that point of view, yes, so clay may actually be contributing silica and alumina and get consumed in the process.
Thank you so much, sir. N. Muthukumaran, you have any doubt, please ask. You raised your hand.
Yes, ma'am.
Yes.
Yes.
Yes, yes.
Yes, ma'am. Very informative session, sir. I have a doubt whether this nano rheology, how it reacts with the normal concrete structures, sir.
I'm sorry, I didn't get the question. Nano rheology, what is it?
How this nano rheology works on this concrete, sir, to improve its strength or durability, or
Yeah, man, let me be clear. Nano-rheology is something different. Nano-rheology is when you're dealing with rheology or flow of a liquid.
Yes, sir.
Yeah, so nano-rheology is when you're talking about flow in a very small capillary, right? And that's typically what people are doing when they're talking about trying to model, say, fluid flow in a blood vessel or something. Because those are very, very tiny capillaries, and then to be able to understand, predict flows there, the one has to understand the physics in a very narrow capillaries, because the physics there changes. So we are not talking about that here. This is not what we're doing. We're just adding nanomaterials to influence the rheology of the paste. That's what we're doing, right? So now coming to durability, there are always issues of durability, and one has to be very careful about whatever you add to concrete to make sure that it does not impact the durability of concrete. So whatever material we add into concrete, we have to look at it in terms of how it performs in the cement system. So just to give you an example, suppose I find at someday that chlorides, something that is a chloride based thing, is very helpful. But I know if I add chloride into concrete, it will eventually lead to corrosion of steel. So these are things that we have to balance out. And in fact, that's what happened. One of the best known accelerators of cement hydration is calcium chloride. And the early accelerators that were used were all chloride based. When people realized that this was like embedding a problem in a concrete structure where it would lead to long-term durability issues, that's when these chloride-based accelerators are banned. So one has to be always careful with all of these admixtures to make sure that they do not produce adverse effects on durability. That has to be looked into. Okay.
Thank you, sir. And one more doubt, sir.
Thank you, sir.
about limestone inclusion instead of cement clinker to some extent. Will it contribute the strength aspect as same as cement hydration process?
Yes. So there is this cement which is called LC cement, which is basically calcined clay. So calcined clay, this when you put it in an alkaline environment, basically gives strength-giving compounds, and this has been tested. Now, what has been done over the past few years is people have optimized it in clinker systems. So when we put calcined clay, we are able to replace cement up to about 50–60% by adding this calcined clay without affecting any property, including durability. So even durability has been studied, and it's been shown that even the durability is not compromised. And the best thing about this calcined clay systems is that we use low-grade low-grade clay, which is basically clay which is not used in agriculture. So that's an alternate cement technology that is slowly making its way. Right, but the chemistry changes when this calcined clay reacts. It forms hemicarboaluminates, not calcium silicate hydrates. It forms carboaluminates, and the strength comes from carboaluminates. So it's a different chemistry that one has to understand.
Anybody else? Anybody else have any doubt? What are one more, sir? What are the different admixtures used for flowability of concrete?
Well, yeah, I mean, broadly, we have the most common class of admixtures we use are the water reducers, right? I mean, you get the mid-range, the high-range water reducers. And of course, now the complexity of these admixtures is very large. We get them, the chemical basis of these admixtures, whether it's polycarboxylate based or naphthalene based, or there are whole others as well that have come to the market. In addition to this, of course, when we want to control the flow, we use admixtures like viscosity modifying admixtures, which are also commonplace now. We're using them quite commonly. So these are broadly the admixtures that we use. The superplasticizers or the water reducers are used to influence the yield stress of the cement paste, whereas the viscosity modifying admixture is used to influence the viscosity of the paste. So we typically use a combination of these two, or one or the other, depending upon how things go. Okay.
Thank you so much, sir. Anybody else? Okay, if anybody is having a doubt, sir, you can post sir, the doubts to sir's mail ID, which will be there on the net. Thank you very much, sir, Professor K.V.L. Subramaniam, sir. In spite of your busy schedule, you have given the time to enlighten us with the various informations in the concrete processing technology, like what are the different expectation of high performance from the concrete, and rheology control of cement paste. And you mentioned about what are the different challenges with the adoption of admixtures. True, sir, it is really a black box. One need to understand exactly how admixture is going to play in, like a role in concrete. One of the way could be possible through this SEM pictures or SEM studies. It is really a very enlightening session for all of us, sir. All our ME students also sitting here who got benefited with your session. Thank you so much, sir.
Sure. Thank you. And if anyone has a question, please do send me an email. I'll try to answer the best I can.
Thank you, sir. Thank you so much.
Thank you.
There is announcement for all the participants. Mostly 50% of the participants are attending the session without your unique ID. Unique ID is already posted in your WhatsApp group. Please join with unique ID only for the next session. Next session will start exactly at 12 o'clock. That session will be dealt by resource person from SCRC Chennai, Dr. S. Bhaskar sir. So he will join exactly 11:30, 12 o'clock, sorry. So try to join five minutes before and fill the Google form and send for second session. Fill the Google form 5 minutes before. Please, all of you fill the Google form and send. After sending the Google form only, you attend the session. Okay. We don't allow you if you attend the session without your this unique ID given to you. Okay. Anybody having a doubt, please tell, or else I'll close the session.
Madam, good morning.
Sir, tell me, sir.
Madam, how to join with ID? Because we are already connected directly by clicking the link.
You should change in the Google settings.
You can remit, sir.
Rename, you can do rename, sir.
Rename means I could not get, madam. Please.
No, in the participant list, madam. Sorry to interrupt you, madam. I can explain to you. In the participant list, go to your name, sir. On your name, click.
Sir, my name is 79. Number is at 79. I am there.
On your name, you keep the cursor, sir. Mouse cursor. It will show the more. Click the more option. There, rename option will come. You rename it. And whatever the file provided in the WhatsApp group by the organizers, you take your unique ID copy, name copy, and paste in your rename. Then it will come as your unique ID name only.
And additionally, this Google form also we have submitted.
Yes, Google form is must, sir, but we should see whether you are attending or not, because ATAL FDP persons are also attending, sir. So we should.
Madam, this joining will not be suffice to that we are we are attending.
No, sir, because if I see some of them are joining with the name iPad and Redmi, so it is not possible for us to trace, sir. Again, we should check your numbers and we should see. So it will be very difficult. It will be very difficult for us to. So please cooperate. Join with only your unique ID.
Okay, madam. One more request. Kindly display the attendance of previous session before next section.
Okay, we'll do that. So sir. We'll do that.
So that we can know where we are.
Okay, sir. Definitely, we'll do that, sir. But for now, for 12 o'clock session, all of you please join with the unique ID only.
Okay, madam.
Okay. Thank you so much. Again, join back the session at 12 o'clock. That means 5 minutes before 11:55. Sharp 11:55. Please join the session.
Thank you, madam. We will join.